4 is approved, and it's posted on the IEEE website. So I'm going to, maybe later today, I'm going to send an email with the link to everyone in the task force, and I'm going to post it on LinkedIn as well. So if you happen to see my post, feel free to repost it or like it so we get as much visibility as possible. Yeah, thank you very much. Back to you, Ravindra.
Yeah, thank you, Sam. So today we have a presentation from Purdue University. So our speaker is Saunan Lu, and he will be speaking on hybrid model-based and data-driven small signal stability and oscillation analysis for modern power systems with complex operation dynamics. So Dr. Lu is an associate professor at Purdue University. He received his BS and PhD in electrical engineering from Tsinghua University. And previously, he has held position at Aalborg University, the University of Tennessee, Argonne National Lab, and Temple University. His research focuses on power electronic inverters, hybrid AC-DC microgrids, and large-scale power electronics dominated systems. He serves as an co-editor-in-chief of IEEE Transaction on Power Electronics and holds multiple editorial roles across leading IEEE journals. His honors include major IEEE regional awards and multiple Purdue Research Awards. So I would pass it on to Shauna.
Yeah, thank you so much, Ravindra, for the introduction. And thank you so much for having me here today. Good morning, everyone. My name is Xiaonan Lu. I am currently an associate professor with Purdue University. As Ravindra introduced, I actually also hold my joint appointment with the Argonne National Lab at this point. My topic today will focus on the small signal stability and oscillation analysis for modern power systems. And definitely we consider the very complex operational dynamics. Okay, so first of all, please allow me to introduce my research group at Purdue University a little bit. Our research group at Purdue University focuses on the ubiquitous power electronics in different applications. Particularly, we synergize power electronics, power systems, applied control, and data-driven approaches for stability, resiliency, and sustainability enhancement. Looking into the details, we highlight two perspectives. The first one is the inverter, power electronics inverter, and in the meantime, we'll also consider the systems of inverters, basically inverter clusters in different applications, such as microgrids or distribution or transmission systems with a high share of inverter-based resources. And looking into the details for the inverter perspective, we look into different types of control functions, such as grid forming and grid following inverter control, and also consider the main power circuit of the inverters for modeling, control, and the design of everything. Basically, we consider the cross-layer dynamics across the main power circuit and also the control diagrams. And in the meantime, we also look into the inverter systems, as I mentioned. Particularly, we look into different types of localized systems covering multiple inverters, or as I said, the distribution or transmission systems with a very high share of inverter-based resources. This includes like the inverter-based renewable energy resources for grid integration, or even the most emerging topics of the data centers, which can be seen as the very inverter-intensive loads. And in the meantime, we also look into applied control theories and also the data-driven based approaches to look into the phenomena of the systems of the inverters. Basically, we look into transient stability analysis and also small signal stability analysis of inverter systems. And in the meantime, we will also develop the data-driven model surrogate to process black box models and other relevant topics. And these are also relevant to what I will be talking about today. Coming to the background, I would say power electronics as our major focus is everywhere. Basically, we see the ubiquitous power electronics in different applications and in different types of resilient and sustainable energy systems. We probably can use a very classic triangle representing power electronics to start this topic, as we show on the top left corner on this page. Basically, we have three aspects of this major power electronics concept, including the power section, electronic section, and my personal favorite, the control section here. And we do have different applications, as you can see, as depicted on this page. For example, for renewable energy integration, we do need power electronics inverters as the interfaces to connect PV panels and wind turbines, for example, to the electric grid. And in the meantime, as another example, for motor drives, we do need to have the motor drives to control the motor speed and the motor torque, among other controllable variables from the motors. And essentially, the motor drives are power electronics inverters. And also, we have the isolated power system applications, such as the electric shipboards or electric aircrafts, where we do need to have the inverter clusters to connect to different types of resources, such as the engines, the loads, and also either AC or DC coupling buses. Back to the buildings, we do have the grid interactive building applications where we need power electronics inverters, so for example, to connect to the backup battery storage units in the basement and also potentially the rooftop solar panels. These are the grid interactive building applications. Last but not least, we need to look into the bottom of this page, which is the application of power electronics in modern power systems. Power systems are really the major values of the applications of power electronics technologies, and power electronics can be used in different sections of the power systems. Zoom in a bit, we can actually look into different sections of modern power systems, including the generation section, transmission section, distribution section, users. Looking into each section of the entire power system, we can clearly see the role of power electronics. For example, for the generation section, we have solar farms or offshore wind farms. Definitely, they are power electronics intensive systems since we need power electronics inverters as the interfaces. And we also have the hybrid power plants, potentially with the solar, wind, or even the battery energy storage systems, where we do need power electronics inverters as the interfaces as well. Going downstream a bit to the transmission section, we actually can see the fax devices. Essentially, they can be seen as the power flow router, for example, or power flow controller, and essentially they are power electronics converters. And also for the very popular HVDC topics, we do need to have power electronics inverters to implement the energy conversion stations connecting the AC section and the DC section. Going to the distribution systems, we see the keywords of microgrids or the medium voltage DC distribution systems, as well as electric vehicle charging stations. We do need to have power electronics inverters in all these applications to be sure that the energy delivery process can be stable and resilient. Back to us, to our home, the end user side. Basically, we have building integrated renewables or the residential level microgrids or nanogrids, where for sure we also see the role and the impacts of power electronics. We talk about power electronics a lot in the background because that is actually the reason and the root cause of why we have some complex operational dynamics in modern power systems. Basically, the power electronics inverters are very useful in terms of interfacing the source and the loads, but in the meantime, they may contribute to the very unique and very complex operational dynamics to the system, so we need to handle them. One typical topic we need to pick up here, which is also the topic of the presentation today, is the scalable small signal stability and oscillation analysis, which is a topic highly related to the complex dynamics and also the dynamics induced by the inverter-based resources here. First of all, let's take a look of what we are talking about here as the major frame we are showing on this page. Basically, we propose and develop the framework to process the large-scale power systems for small signal stability and oscillation analysis. And this work is in collaboration with the National Laboratory of Rockies and also a whole bunch of industry and utility partners as well. For the details of this developed framework, we have different sections here. The first section is very straightforward. Basically, we need the data, we need the input to feed into this tool we are developing here. Particularly, we need the parameters and the models of the synchronous generators, inverter-based resources, the loads, and even the power network. And then we can move to step number 2, which is actually the extended power flow calculation. Because we are talking about small signal dynamics, so we first need to select a given operating point. That's actually very critical since we need to actually perturb the system starting from that given operating point. So we actually propose the extension of the conventional power flow calculation to consider the dynamics from both the control layer and the main power circuit. We'll introduce the details in the following pages. And we move to the very critical part of this developed framework, which is the modular small signal modeling section. In this section, actually, we treat each type of source or load or even the network section as a module. So basically, we can use a small and modular state space equation to represent each module, such as to represent each grid-forming inverter or each load or even each power line section. And in the meantime, we do need to assemble everything to implement the entire system model to integrate all the smaller modular components we developed. From that perspective, so we need to develop the way to assemble the entire system model considering the information exchange and the way of integrating different smaller matrix coefficients and putting them into the bigger matrix, such as the A matrix we are looking into for small signal stability analysis. And coming to step number 4, which is a very important and very natural last step, which is to get the outputs and outcomes from this tool. Basically, we focus on the stability analysis here, small signal stability analysis particularly, and we highlight eigenvalue analysis to identify the small signal stability margin of the system, considering the impacts of inverter-based resources and loads. And in the meantime, we will also have the model analysis outcome, which focuses on identifying the specific oscillation modes of the system. And also the participation factor is another tool where we can identify the root cause of the oscillation modes, and in the meantime also the troublemaker of the system, saying that that unit may be contributing to the critical oscillation modes we identified. And the last one is the quantifiable stability indicators we can develop and incorporate into other grid applications such as AC or DC OPFs for the small signal stability constrained OPF. For this type of the issues and research questions, we actually look into the cross-layer dynamics. Conventional approaches may focus on the physical layer, meaning that we considered the grid-forming IBRs, synchronous generators, grid-following IBRs, and loads, and also network, basically typical types of resources in the physical network, physical power network. But this is not the end of the story. Basically, we are talking about like very complex operational dynamics in the system, meaning that the control dynamics are actually highly coupled with the dynamics from the physical layer, meaning that we also need to consider the state variables at the given operating point, and also the contribution from the control, and also the operational dynamics contributed from the control layer. So that's actually a cross-layer solution, which we look into and also incorporate into our developed framework. Some very boring and or very fundamental knowledge for small signal stability analysis. Basically, we can use differential equation set, a general one, for example, as we show on this page, to represent the dynamics of a given system. And also, like a textbook definition, we can use the vector form to represent this system and perturb the steady state values by involving some very small disturbances. And then we can leverage the partial differential terms of the system to basically convert the original system, focusing on the given operating point and the added very small perturbation, and definitely the high order perturbations are ignored, and eventually we can get linear small signal models. This is actually the textbook definition. I'm showing that because we are starting from here, from the scientific basis here, to basically develop our approach. And our approach can be shown from different perspectives, as we mentioned. The first one is about the power flow calculation. As we mentioned, we do have the extension of the existing and conventional power flow calculation scheme. For example, let's take frequency as the first very straightforward example. In conventional textbook power flow analysis, basically frequency is treated as a constant, such as 60 Hz or 50 Hz. But in the extended power flow calculation, we need to understand that we actually have a grid forming inverter units there, meaning that the frequency can be regulated actively. So to capture all sorts of dynamics from the system, we actually treat the frequency as a variable rather than a constant. Conventional systems may also have some differences or perturbations in frequency, but generally it's not like, the perturbation contributed from, like, for example, millions of inverters or a whole bunch of resources that can regulate the frequency for a very high, relatively higher frequency. So frequency as a constant is reasonable, but here we do not want to miss any dynamics since we have highly complex operational dynamics in the system. So we treat frequency as a variable. And accordingly, the type of the buses can be extended to include, for example, the node and the bus where the frequency and voltage can be changing, such as the grid forming bus or grid forming node, and also accordingly, the power injection or consumption are not just simply constant. They can be shown using a relatively generalized format as we defined represent different types of buses, including the new types of buses we considered here. Since the frequency is a variable, actually the Jacobian matrix need to be extended in further, since we need to have the partial differential term of the frequency as well to capture the dynamics of the frequency and incorporate it into the small signal stability analysis. And as I said on the previous page, control systems are very critical since they contribute to this complex operational dynamics, and these dynamics are highly coupled with the original of the dynamics from the original analysis we look into in the conventional systems. So we do need to consider the impacts of all sorts of control systems. Back to some details. For step number 1 of the extended power flow algorithm, we definitely can look into the Newton-Raphson approach. This is actually a very conventional method for power flow calculation, but for the steady state values we would like to calculate and extract from the system in step number 2, we do need to consider more things. The first thing is the inverters. On the left bottom corner, basically we show the general equations of the inverters to capture the model of the inverters from the main power circuit perspective. And then for coordinate transformation, DQ frames are very commonly used. But think about that. If we have millions of resources in the system, we may have millions of DQ frames in the entire system for small signal stability analysis. So the very critical and very straightforward requirement is we need to synchronize them. So we need to synchronize these DQ frames to the common capital DQ frame there. And also back to the third category, we also need to consider the steady state value from both the main power circuit and the control diagram. As a very typical example here, even for a simple PI controller, the integral term will contribute one state variable we need to consider here. So that's actually a typical example of the state variables and the dynamics we need to extract and consider from the control diagram. Okay, let's take a look at two common examples of different type of resources we need to identify and consider. The first one is the grid forming IBR units. We are showing a very full picture of the droop-based grid forming IBR here, including the main power circuit of the inverter and also the detailed control diagram. I'm not saying that for any cases we need to include all the details here in this picture for representing the control details of grid forming IBR. But I'm just saying that this is a full picture with all the components considered, so we can pick what we need, such as the voltage control loop, the current control loop, the droop controller, and even the virtual impedance control loop here. And for the grid following IBRs, we are actually also using a typical example here, including everything, such as the outer power control loop to regulate the active and reactive power with dedicated PI controllers, and also the inner current control loops for ID and IQ control. And definitely we have the phase lock control loops, phase lock loop considered to track the grid voltage phase angle and even the frequency. And this is actually a typical grid following inverter model. As I said, looking into different types of models, we can actually implement the state equations of a different unit, and power flow analysis is generally in the very traditional way shown in this way. But unfortunately, this is not the end of the story. Because we are talking about scalability, the system is very large. If we just simply put everything, we develop each part and put everything all together for power flow analysis, and we probably can implement this flow chart easily. However, when we actually run it, it could be extremely time consuming. So we do need to have some algorithm optimization efforts here for improving the computational efficiency. Surprisingly, the very critical and very useful way of improving the computational efficiency is actually very straightforward. Basically, for example, for the conventional power flow equations, the very straightforward and very easy way of implementing these equations is to use multiple cascaded for loops or while loops, which is doable, which is straightforward, but it's not very computationally efficient. What we can do is actually to dive into the details of how each step is implemented in the code and actually convert multiple cascaded for loops or while loops using the matrix operations and define some matrix operators as well. That's actually a very efficient way of improving the computational efficiency. And the same technique can also be applied for the Jacobi matrix, can also be applied to the Jacobi matrix calculation as well. I will show some case studies to showcase the room for computational efficiency improvement. And after developing the smaller modules, after calculating the power flow following an extended version, as we mentioned, the core of this small signal stability analysis is basically the way of assembling the larger A matrix using the smaller matrices coefficients we developed for each model. Okay, we look into the details of how this thing can be implemented, and the way of assembling the smaller matrices into the bigger one are detailed here. So basically, we look into the generator section, load section, and also the network section. The way of putting together the smaller matrix coefficients to form the larger matrices. The scheme is depicted on this page. Let's maybe take a generator as an example. We have A, B, and C matrices to consider. For the A matrices, we basically just need to capture the diagonal elements in the bigger matrix to put the smaller elements along this line. And in the meantime, for B matrices, it's mainly around the center between J1 to J2, the selected two nodes. And in the meantime, the way of assembling the bigger B matrix is also depicted on this page. And for another B matrix related to the frequency dynamics and the common frequency on the common frequency frame, basically it is like a vertical vector to put everything all together. And also back to the C matrix, which is related to the output, we actually also take the diagonal elements from the bigger matrices to put to place our smaller C matrices from the original modules. For the load and the network sections, for the loads and the network sections, we actually can follow similar approaches to assemble the bigger matrices there. Okay, if you have some experience developing this type of small signal stability models, for example, back to around, if I recall correctly, around more than 10 years ago, actually people talk about the small systems such as microgrids to develop the small signal models, which are very useful work for sure. And you probably know that there may be kind of like there could be an inconsistency between the numbers of equations and numbers of state variables. That is actually true. And the way to handle that is to add another very large virtual resistance representing kind of like the resistance connecting each bus to the ground. But the resistance, the virtual resistance, let's say it is Rx, is really large. So essentially from the physical perspective, it is not there. It is just for processed mathematical calculation to have the same numbers of equations and the same numbers of state variables there. And eventually, the way of handling that is also shown on this page. And since this virtual resistance is added, and connected to each individual bus, we also need to define a way of assembling the smaller Rx matrices into the bigger ones. And the way of doing that follows the same route and scheme as we developed and identified on the previous page. With all these preparations, eventually, that is actually a very exciting point. We can actually develop the very big A matrix for the holistic small signal stability model. Basically, the smaller units are assembled and then eventually assembled again to find the bigger A matrix here. And you probably can see that with some brief review of this bigger A matrix, we can actually identify the coupling terms or the individual terms across the different units. Then let's talk about the outputs or the outcomes from this tool. Again, we focus on small signal stability analysis, and the first outcome and the first output is very straightforward, which focuses on the eigenvalue analysis. Basically, we can extract all the eigenvalues from the derived holistic A matrix and to identify the system's small signal stability margin and also identify if or not the binary decision that the system is stable or not, the stable or unstable. And for output number two, the outcome number two, which is also very critical, that is the model analysis, where we can actually extract literally all the oscillation modes from the system and identify the corresponding oscillation frequency and the damping ratio of each oscillation mode. And that is actually the way for us to identify, for example, some critical oscillation modes in the specific systems with specific scenarios. And back to output number three, we actually focus on the participation factor analysis. We can use a heated map to showcase the contribution of different state variables to different types of oscillation modes. As you may imagine, this is actually a way to identify the root cause of each selected oscillation mode and also to identify the troublemaker of the system. For example, the state variables from inverter-based resource number one could contribute to the oscillation mode number one. And then we know that actually we can do something to the inverter-based resource number one to potentially lower down that troublesome oscillation modes. So that is actually the way to identify the root cause and, in other words, the troublemaker of the system in terms of triggering the oscillation modes here. And for the output number four, we focus on the extension of the horizon and research outcomes from this work. Basically, we can define the quantifiable stability performance indicators, which can be further integrated into different other applications, such as OPF schemes. For example, typical indicators can be defined as first, stability margin, very straightforward. Basically, we highlight and identify the maximum real part of all the eigenvalues and also get a minus sign there to convert it to a positive value for easy incorporating into existing power flow analysis schemes. And also for the typical indicator number two, we can focus on the minimum damping ratio of the system. Basically, it represents the minimum damping ratio of the oscillation modes identified from the system. And these two examples are just examples. Basically, the quantifiable stability performance indicators can be freely designed, or for example, we can combine the indicator number 1 and indicator number 2 to highlight our specific focuses in specific applications. Okay, now let's look into some case studies and applications. The first one, as what I mentioned before, is to echo the computational efficiency improvement, where we actually look into different types of the system with different numbers of buses, ranging from the 9-bus system to over 2,000 bus systems. And as we can see that with the numbers of buses increasing drastically, definitely, as we may imagine, the time needed to finish this calculation increases accordingly for sure. But in the meantime, if, for example, we replace the for or while loops, the cascaded for or while loops with matrix optimization or matrix operations, basically the computation time can be significantly reduced. And in the meantime, if we look into a more detailed analysis, for example, we can use fsolve as the baseline case for power flow calculation, and then we can incorporate a Jacobian pattern to incorporate the sparsity of the Jacobian matrices. And we can actually also incorporate the matrix operation. As shown on the right side, we actually can see that the computation time needed for each step of the power flow calculation can be significantly reduced as well. So this is the results to echo the computational efficiency improvement efforts. And also for case study number 2, we highlight the guidance provided from this tool for parameter tuning. Basically, let's use a small system this time to highlight this role so we can see some more details here. So basically, let's take a 2-machine system with a Drupe-based grid-forming inverter-based resource and also synchronous generator. We actually can use the tool to identify all the oscillation modes from the system. For example, the one with around 0.93 Hz oscillation frequency, and also we can identify the dominant states with a relatively smaller damping ratio. And we can identify that this is actually a coupling mode or a coupling oscillation mode, where we need to consider the contribution from this, the synchronous generator and also the inverter-based resources. And this is not the end of the story. As we mentioned that we can actually further identify some guidance or recommendations for parameter tuning to basically, for example, dampen this oscillation mode to some extent or improve the system stability margin accordingly. For example, we already identified that inverter-based resource is actually related to this oscillation mode. So we can play with the corresponding control parameters to actually increase the stability margin and potentially, and also accordingly, lower down the impacts of this oscillation mode accordingly. Another example is about the impacts on the system impact analysis. So for example, to identify the role of grid-forming units in terms of contributing to the small signal stability enhancement in the overall system from the overall system perspective. As we can see that we actually use a sample system with 4 IBRs, 3 synchronous generators, 8 loads, and 23 lines as an example. And what we are trying to do here is to gradually replace the grid-following inverter-based resources with grid-forming IBRs, and we see if there are any impacts from the system stability, small signal stability perspective. Let's take a look at the figure on the top right corner. Basically, let's look into the magenta curve first. For the magenta curve, actually at the beginning, we have 0 grid-following IBR replaced with grid-forming IBR. And we can see that unfortunately the system is actually unstable. And in the meantime, for the next step, we replace 1 grid-following IBR with a grid-forming IBR, and the system currently has actually a mix of grid-forming and grid-following IBRs. And we can see that actually the system stability margin, as we define it as the quantifiable indicator, increases drastically, and the system is likely stable now. And then if we keep replacing the grid-following IBRs with the grid-forming IBRs, we can actually see the system stability margin increases accordingly, which is great. And this similar trend can be also captured with a different system inertia age ranging from 0.5 to 1.5. And also, accordingly, for the minimum damping ratio, we can define actually similar phenomenon can be captured with zero grid following inverters replaced with a grid forming one. Actually, we have unfortunately an unstable system from small signal stability perspectives. But if we gradually replace all the grid following IBRs in the system with the grid forming IBRs, the system damping ratio, the system minimum damping ratio increases as well, indicating that the system is stable from small signal stability perspective. Okay, after looking into the case studies, let's also quickly go through an automation process. We definitely would like to automate the entire process to make the tool more user-friendly for sure. And here we actually focus on the EMT model implementation to make sure that we can capture all the dynamics from the system to echo the complex operational system dynamics there. And we would like to look into the large systems, such as in collaboration with the National Laboratory of Rockies. We are actively working on the large-scale system analysis, focusing on the WAG 240 system, which is a very useful deliverable from the National Laboratory of Rockies. And actually, the automation process, including the parameter extraction, the data integration, and even the model conversion from commercial tools such as PSSE, can be done automatically. And also, for the smaller model implementation and also the model assembling process, they can also be automated for sure. And also, very interestingly, we can actually look into some additional approaches to basically further increase the computational efficiency, further improve the computational efficiency. For example, to use some additional eigenvalue calculation or acceleration approaches to calculate the eigenvalues in our target frequency range. Also, data-driven based approaches need to be considered because actually what I introduced from all the previous pages are actually focused on the model-based solutions. We are actually giving this presentation in the task force on digital twins. Ideally, or by definition, actually the model-based solution, the entire small signal model can be seen as a digital twin to give the operators the information of a small signal dynamics of the original system. However, even though we can satisfy that part of the needs, we actually need to identify some specific challenges in the real-world implementation. Specifically, when we talk to multiple developers, the vendors, and the system operators and the utilities, we actually know that there is a kind of like a natural conflict between the developers and also system operators when we talk about interconnection studies, meaning that basically the vendors and the developers in most cases can only provide the vendor-specific black box models to the system operators, and especially for the EMT implementation or EMT models. And this part of the EMT models might give us or give the system operators some sort of information, but the parameters can be tuned or the dynamics they can see, the operators can see are very limited. So basically the transparency is kind of like a concern, which is understandable given that we need to protect the developers and the vendors need to protect the trade secrets, but it's really a challenge. So the way of processing the black box models is actually something we recently implemented, which has just been published in the latest journal, in the latest version of IEEE transactions on power electronics. So basically what we are trying to do is to break the black box model to basically develop the data-driven model surrogate to represent the dynamics of the system. However, I have to say that for the conventional black box modeling efforts, basically people focus on the input and output mapping, for example, using a neural network. But this type of approaches may lack the capability of capturing the intrinsic dynamics where we value a lot in small signal stability analysis. So to do that, instead of using the neural network to only represent the input and output mapping, we actually develop and use the neural ODE to capture X dot, because X dot is very needed in our small signal stability analysis. And this is also not the end of the story. Knowing that our target is to guarantee that the developed model surrogate and the original model can give us ideally identical results from small signal stability perspectives. So we actually also incorporate or impose an additional term in the training process of the neural ODE to basically guarantee that the small signal characteristic of the original model can be preserved in the developed neural ODE. With that considered, we actually use the Jacobi matrices to actually capture this intrinsic dynamics that is directly and highly related to the small signal dynamics. And with this additional term added to the training process, we can actually capture the results and the trend, the neural ODE that can preserve the small signal characteristic as well. So eventually, our developed data-driven black box model surrogate can capture the large signal dynamics for sure, as all other types of black box modeling approaches can do. And in the meantime, we also preserve the small signal characteristics from these black box models to ensure our specific application of small signal stability analysis can be satisfied. Here's some further reading for the work we introduced. We already fully published the work as we introduced in this presentation, including the work on the model-based solution with our collaborators from National Laboratory of Rockies. Here we focus on the holistic small signal stability analysis and also pick a hybrid power plant as a specific example to highlight the effectiveness of this approach. And in the meantime, for the most recent work, we actually look into neural ODE modeling to process the black box models. And as we mentioned, we incorporate the small signal characteristics into the neural network training process to successfully capture the latent feature from the original system. That's actually for this new part of the work to process the black box models, and the details of the papers are shown here. Last but not least, we would like to express our special thanks to the contributors, including the National Laboratories of Rockies and also my internal team from Purdue University for the majority of this part of the work. Thank you. Yeah, Robin, I probably give it back to you. Yeah, thank you.
Thank you, Sean, for providing a framework for small signal stability in inverter-dominated power system. So now we have time for questions. So please ask your questions.
Hello, this is Hussein. I have a couple of questions. Shana, first of all, thank you very much for the informative presentation. I have two questions actually. On one of your slides, you were talking about different modes of oscillation, local versus coupling. And I was not very sure from that slide how you could differentiate between these two kind of modes of oscillations.
Oh yeah, actually for that perspective, we mainly focus on like if it is the oscillation mode, for example, I believe you are talking about this page, right?
Yes, right.
Yeah. Okay, so specifically, the definition could be different, but what we are talking about here, speaking of a coupling, we talk about if it is kind of like, include the contribution from dominant state variables from different units. That's actually something we are talking about. For example, if we see, hey, this state, first of all, we can identify the dominant states from the system. And if we see that the dominant states cover both the synchronous generator and the inverter-based resources, we define them as a coupling oscillation mode. The reason for that is actually we try to identify the motivation of this work is we try to identify how we can mitigate some oscillation modes. So identifying that this oscillation mode includes the coupling contributions from different units, or the contribution only from the one individual unit could be helpful. So that is the way for us to define different types of the oscillation here.
Okay, thank you for that. And then
Sure.
the other question is about just trying to understand this methodology on a high level. So traditionally, the way that we do small signal stability is that after we do the power flow, the traditional power flow, then we can create the small signal model of the physical layer of the component as well as the control. So for example, if I want to look at the variation of the frequency, I can use the swing equation of the synchronous generator, create the small signal model out of that, and then on top of that, I can add the another block for the, let's say, for the turbine, and then governor on top of that, and even AGC. So these diagrams are pretty available in many of the reference books. Now, is in this methodology, are you trying to somehow mirror power flow and this small signal stability in one platform, or what is the difference? I couldn't follow. Yeah.
That's a great question. Thank you so much. So basically, the overall steps and the framework is actually the same. I would say that. But probably I didn't explore all the very specific steps in all the conventional approaches. But generally, based on your descriptions and my knowledge in my review, I would say the general steps are the same. But there are differences. For example, per our understanding, for the existing small signal stability analysis, we mainly focus on phasor domain analysis. That's actually something that could trigger an issue if we have very complex operational dynamics in the system. So that's the reason that we say we actually focus on the EMT models, the high fidelity models, to basically capture everything. That is actually, as I said, in collaboration with the National Laboratories of Rockies. The researchers there lead the efforts with targeting the very inverter intensive utilities and the very inverter intensive systems for identifying the featured oscillation modes. So that's actually the reason that we accordingly developed this EMT-based high fidelity small signal stability analysis to echo the oscillation modes we can identify from the field. That's one thing. And another thing is about the scalability. So basically, we try not to miss the fidelity of the models, meaning that we stick to EMT models. And in the meantime, as you must know, the computational efficiency of EMT models or the large-scale EMT models is always a concern. But we are doing more, actually. We are not only capturing the EMT models of the original system, but also conducting the small signal stability analysis and also the oscillation analysis based on the large-scale EMT models. So the computational challenge is definitely a concern. So the second part of the difference of our work is basically scalability. So that's the reason that we specifically look into the modular configuration in this work to be sure that the computational burden can be shared in different steps and in different units, and eventually it can be done. So that is actually another major part I would like to highlight and potentially contribute to your question regarding the differences.
Yeah.
Yeah.
All right. Thank you very much. I appreciate it.
Thank you. That's definitely a very valuable question. I very much appreciate it. Thank you so much.
Yeah, any other question? Please raise your hand if you have questions.
Hello?
Hello?
Hello, this is Jean Bélanger here. So thank you for this very, very good presentation. It's a very good overview of your algorithm. Can you explain more about the black box identification that you succeed to get at the same time, the large system disturbance and the small signal model?
Yes, thank you so much. I really appreciate that question. And actually, for that part of the work, basically, Okay, so first of all, we use a neural ODE to represent the black box models, meaning that we see the black box models and we try to know something more about the dynamics, but we couldn't given the lack of transparency. So we try to develop a model surrogate to represent the model. The idea is actually straightforward. And to do that, we evaluate different types of data-driven models we may use. And we noticed that the input and output mapping, which is commonly used as neural network to represent black box models, may not be very suitable for our work, since we actually need to highlight X dot there for small signal stability analysis. So we selected the neural ODE. That's the first step. And in the meantime, given our specific application is a small signal, is to capture the small signal dynamics. So we try to preserve the small signal characteristic during the neural ODE training process, which is currently not covered in the conventional neural ODE training process. And that means after doing this, after finishing this training process, the small signal characteristics such as the Jacobian matrices or the location of the dominant poles can be preserved from the original system on the fly. And eventually, the consistency in terms of small signal stability characteristics can be preserved comparing the developed neural ODE and the original system. That's actually our approach. And the paper has been just published in is this one actually on the right side on the latent feature informed neural ODE modeling for lightweight stability evaluation of black box grid tied inverters. This is published in IEEE Transactions on Power Electronics. But this is a very great question for sure. I'd be more than willing to help some follow-up discussions on that if needed. Thank you.
Thank you. Thank you very much.
Thank you.
Any other question? Sanan, I have a question for you. So, I mean, in inverter or IBR-driven power system, so inertia drops, right? So, can you comment on the impact of that and what is the strategy for control system design to mitigate that impact?
Oh, thank you, Ravindra. Just to confirm, are you saying the converter design, or is I talking about hardware, or I'm just trying to capture the details of your question?
No, so I mean, what control actions are needed in order to mitigate the impact of low inertia in the grid?
Okay, that's definitely a very good question. So in terms of the control needed, we actually look into the grid forming inverter. So for sure, that is not only a project need, but also per our understanding, because the grid forming inverters can actively contribute to regulating the frequency and the voltage and make the integration of a grid of inverter-based resources easier. So that's actually what we do. And in the meantime, damping is potentially something we need to consider as well. And the damping control, such as the way to dampen the low frequency oscillations or the relatively higher frequency oscillations in very inverter intensive systems, can also be incorporated into the existing grid forming control functions, such as the typical approaches we use include water resistance or to tune the relevant parameters. But these are actually some common approaches we can use to dampen the oscillations. Maybe a typical example can be related to the very emerging applications in data centers. Basically, the data center is essentially inverter intensive system. Some oscillation modes could be different, and it could be somewhere attenuated inside the data centers to minimize the impact to the external grid. Yeah, hopefully that can cover at least a part of your question there.
Yeah, thank you, Sanan.
Thank you so much, Ravindra.
Yeah. Any other questions? Yeah.
Yes.
Gene.
Yeah.
Yeah.
When you evaluate the participation factor, are you trying to also to evaluate the effect of the operating point?
The short answer is yes, but it's actually a two-step solution. Basically, when we say impact factors, when we say participation factors, basically we actually get a map but that's actually a map or a snapshot based on the given operating point. But if we change to another operating point, we need to restart. We need to restart the process to get a new snapshot and a new heat map to identify the impacts of different units. That's what we currently work on.
Thank you. I have one last question.
Please, I like the questions. Thank you.
I have one more. You mentioned that you have an automatic interface from PSSE, for example, to generate the EMT, and from the EMT you compute your eigenvalues. But do you have an interface directly from PSCAD or EMTP where you have big models made with the nodal solver? And
that's
how? Yeah. So
sorry. Go ahead. Go ahead, please.
So I mean, so you have a way to extract the eigenvalues out of the nodal matrix and the controller given by the PSCAD. So
yeah, that's definitely a very good question. Thank you for that. Basically, I would say first of all, let me clarify. This is actually some ongoing work to basically consider this kind of practical or even commercial questions, to interface with the different commercial tools. I would say now we can interface PSSE, and it's not like, I wouldn't say it's a fully automated process at this point, but we are developing that, and it is kind of like almost an automated process. And in the meantime, for for other software tools like EMTP or PSCAD, that's definitely our goal to do that. But it's currently not implemented yet, but that's definitely on our radar for sure. And probably all party has the interest, and we can definitely have some more in-depth discussions on that for sure.
Yeah, thank you. Thank you very much. Will you share this?
Thank you. I appreciate the questions. Thank you so much.
Will you share this presentation?
We'll see. We'll need to seek some sort of consent first for sure. Yeah.
Good.
Thank you.
Okay. Any other questions? If no, then we conclude this meeting. So, Anand, thank you very much for the great presentation, and thank you all for attending.
Thank you very much.
Thank you. Thank you so much, Roger, for having me here. Thank you, everyone. Thank you.